let's look at calculus. So let's take a function, and as an example function we'll use y equals x squared. And let's ask ourselves, at some particular point, at some particular x, what's the slope? So if we draw a tangent line, what's the slope of that line? So slope is the change in y divided by the change in x. Change in y, change in x, slope equals change in y over change in x. So let's redraw this section and spread it out a bit so we've got space to work with. Here's our x. So what we can do is we can move along a distance h, and we could calculate the slope of this chord. Which is going to be what? Well, the change in x is just h, and the change in y, what's this length here? Pause the video now and see if you can figure it out yourself. Okay, so it's just the y value here minus the y value here. So what's the y value here? Well, this is x plus h, so this is going to be x plus h squared. And can you finish it off now? This is going to be x squared, because this is y equals x squared. Whatever x is, we square it. And so this is just well, what is x plus h squared? X plus h times x plus h, which is the same as x plus h times x plus h times h, which is xx plus hx plus xh, which is another hx. So we've got x squared plus 2hx, and we've also got an hh. Okay, so the slope equals change in y over change in x equals all of that, x squared. We didn't subtract that, we just calculated that. We expanded out this to get this. So that minus that is just 2hx plus h squared, because the x squared, we've got that minus x squared, which is the same as that minus x squared, which is that, minus x squared, which is just 2hx plus h squared, because that cancels. So 2x h plus h squared over h, which is equal to what? 2x plus h. Okay, now what's going to happen as we shrink this down towards x, as h shrinks towards 0? So as h shrinks to 0, our slope approaches to x. So in the limit as h tends to 0 of our slope is equal to 2x. And we can also write this as dy by dx, which is the limit as h tends to 0 of change in y over change in x. Otherwise known as our slope. Okay, so what if instead of y equals x squared we had y equals x to the k? So now change in y is going to equal x plus h to the k minus x to the k. And if we expand our x plus h to the k, you can imagine we've got x plus h, and we've got k of them. Okay, so if you take the x here and the x here and the x out of each one, you get x to the k. And now let's take the h out of this and the x out of everywhere else. So we've got h x to the k minus 1. And now let's take the h out of the second one and the x out of everywhere else. And we've got another one, and so on. So we'll end up with k of them. K lots of h x to the k minus 1 plus, well, every remaining term has at least two h's in it. Like we're taking the h out of this expression, and we're taking the h out of this expression, and we're taking the x's out of everywhere else. That's got two h's in it, so it's terms of order h squared. Yeah, every term remaining has at least two h in it twice. So change in y by change in x, or change of, we forgot to put that minus x to the k, minus x to the k, so that's going to cancel. Oh, change in y over change in x is equal to this over h, so that's just kx to the k minus 1, plus, well, if every term here had an h squared in it, and we're dividing by h, still every term is going to have an h in it. And what's going to happen to this thing as h shrinks to 0? It tends to 0 as h tends to 0. So dy by dx is the limit as h shrinks to 0 of that thing which is just this, k x to the k minus 1. What about y equals x to the k over k factorial? What's that going to differentiate to? Well, that's just 1 over k factorial, which is just some number, times x to the k. So if we had our function y equals x to the k, and we know the slope at this point is s, so change in x is 1, change in y is s. Yeah, change in y over change in x is s over 1 is just s. So at this particular x, we say the derivative of y dash at x, is equal to s. So question, what's going to be the slope of y equals 10x to the k? What's going to be y dash at this particular x? Let's call it x0 just to show it's a particular x. See if you can figure out what that's going to be in y. Okay, well, by multiplying by 10, every single point here gets replaced by a point 10 times greater. So it's going to be so this triangle is going to turn into, maybe 10 was a silly number because I can't draw it very well, but can you see the new triangle is just going to be 10 times the height and the same width, because we've effectively stretched everything by 10 times. Yeah, we've made all the numbers 10 times as far away from the x-axis as they were. So if this was here, now it's 10 times that. So if we have k f of x, and we differentiate it, it's just the same as k times f dash of x. So this is our constant. So if we differentiate that, we can just move that out, 1 over k factorial x to the k dash, which is 1 over k factorial times k x to the k minus 1. Now, can you see why we chose this originally? Because what's k factorial? That is just k minus 1 factorial times k, isn't it? Multiplied by k x to the k minus 1, and these k's go, and we're left with k x to the k minus 1 over k minus 1 factorial. And this is a really nice result. It's much tidier than this result, x to the k goes to kx to the k minus 1, because it has a symmetry to it. X to the k over k factorial differentiates to x to the k minus 1 over k minus 1 factorial. If you don't remember factorials, here's a quick primer. 4 factorial is 1 times 2 times 3 times 4. That's 4 factorial. So 5 factorial is 1 times 2 times 3 times 4 times 5, which is the same as 4 factorial times 5. That's what we've done down here. We've just split k factorial, split off the k minus 1 factorial times k factorial. Now, what if we take some function which is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... all the way to infinity. What's going to happen when we differentiate that? Well, let's look at the kth term, x to the k over k factorial plus ... Can you see that these first two terms are just k equals 1, x to the 1 over 1 factorial is just x, and x to the 0 over 0 factorial, x to the 0 is 1, and 0 factorial we define as being 1. So that's 1 over 1. So this is the general term. So can you see it's just going to shunt itself back? 1 is going to differentiate to 0, x is going to differentiate to 1, x squared over 2 factorial is going to differentiate to x to the 1 over 1 factorial, x cubed over 3 factorial is going to differentiate to x squared over 2 factorial, so this function differentiates to itself. And this is a very special function in maths, and we call it the exponential function. Define the exponential function as that function, the sum from 0 to infinity, x to the k over k factorial I don't really need to write k equals 0 to infinity. Just because I'm using k inside, so it's obvious it's k. If you're not familiar with this sigma notation, it's summing. So the sum from 1 to 3 of I squared is going to be what? 1 squared plus 2 squared plus 3 squared. Yeah? This is sigma notation. So if you look at a graph of this, it has the property that at any x value, so say x equals 1, the slope is equal to the y value. So this is x per 1 and the slope at this point will also be x per 1. Similarly at 0, what's the slope going to be at 0? Well, it's just the x of 0. And what is x of 0? Well, 0 means all of these terms are 0, leaving just the 1, so x of 0 equals 1. And x of 1 we write as e, which is one of the maths constants. It's equal to 2.718281828, and then it goes off the rails. It's a transcendental number. It never repeats. There's no pattern to the digits after that. You will find we can eventually write x per x as e to the x, although we haven't shown that yet. We haven't been entirely rigorous because we haven't shown that this sum, this infinite sum, always converges. For example, if you threw in x equals 10,000, it's possible that maybe this infinite sum would be itself infinity, and therefore f of x wouldn't have a definite value, and we wouldn't be able to differentiate it, because at no point in our argument here did we consider f of x being infinite. The argument would break down if it was infinite. So additionally, we would need to prove that for every x, this comes out as a finite number. And that's not too hard to do, because each time we're adding a positive number, let's suppose we're looking at positive x for the moment. So if we rewrite this a slightly different way, f of x equals 1 plus x squared over 2 factorial plus da da da. Let's write that as 1 plus our original 1 times x over 1 plus 1 times x over 1 times x over 2 plus 1 times x over 1 times x over 2 times x over 3 plus dot dot dot. So we're trying to show that this converges for every x. So we suppose the opposite. Suppose it fails for some x. So can you see eventually we're going to reach a term where we've got 1 times x over 1 times x over 2 times ... times x over the next number greater than x. So if x was 17.3, it would be 18. So let's call that rounding x up to the next integer is just the CL of x. That's the symbol for it. And now every term after that is going to be multiplied by a number smaller than 1. So let's be more extreme and say you go further down the sequence. Eventually you'll reach the point where we've got 2 CL of x on the bottom. Okay, so this number here is less than a half. But the next term is going to be that term multiplied by x over 2 CL x plus 1. That thing's also going to be less than a half because the number on the bottom is bigger. So it's going to be even smaller than this, and this was less than a half. So that is also less than a half. So can you see where we're going here? Every term in the sequence is going to be less than a half of the previous term. So if this term had a value t, then all the terms that follow is going to be t plus a half t plus a quarter t plus ... which is the same as t times 1 plus a half plus a quarter plus ... And if you take 1 square and then a half a square and then a quarter of a square and then an eighth of a square and a 16th of the square and so on, the limit is 2 squares. So the limit of this is 2t. So f of x is less than all of this stuff plus 2t, which is a contradiction because we started off by saying suppose it fails for this particular x, and now we've shown that actually it has to succeed for this x because it is just this, which is some finite number, plus 2t, and t is another finite number. So therefore it can't fail for any x. So therefore x converges everywhere. Okay, let's put some headings in. So, differentiating x squared. This was differentiating x to the k. This was differentiating x to the k over k factorial. This was the exponential function. And this was a proof that the exponential function converges everywhere.